Hello class. Today we're talking about heating and cooling curves. This is a very short lesson followed by a video lab. I videotaped our quick little activity we were going to do, and it allows you to continue and kind of see what happens. So today we're talking about heating and cooling curves. So heating and cooling curves are when you heat a substance, it is going to warm up. It will eventually, if it's a solid, melt, and then it will heat up some more, and then it will evaporate. And then you can keep heating the gas if you have it inside of a container, and it can continue to heat from there. During the melting or the evaporation, remember the energy is going to go into breaking the intermolecular bonds. We talked about this yesterday and calculated this using the latent heat of fusion and vaporization. That means that at that point, when it is actually breaking bonds, instead of the heat causing the molecules to move faster because they gain kinetic energy, instead the temperature will remain constant during that change of state. And that is because during that change of state, the heat you're adding is going to break the bonds. Of course, as soon as the change of state is finished and everything has melted or evaporated, then the heat will cause a temperature change again. What this looks like when it comes to a curve, which is just a graph, then you'll notice I've put the temperature on the side and the time along the bottom. As I heat the substance, it gets warmer and warmer and warmer. The molecules move faster and faster and faster as it heats up, and the temperature will increase because remember, temperature is purely a reading of the speed of the molecules. Once it hits its melting point, so if this was water, this would be 0 degrees. Other substances, of course, have other melting points. During that time in which it's actually melting, the temperature will not vary very much. It will basically stay the same. And that's because as it's melting, that energy going into the system is breaking bonds, breaking those intermolecular bonds, reducing the attraction between the molecules, and it's not going to go into speeding up the molecules. Then, once it's all melted, melting has ended, you keep heating it, that will actually start changing the temperature again. The temperature changes again as it heats up, the temperature will increase because those molecules are moving faster and faster, and that is what temperature measures, the speed of the molecules, until we hit the evaporation point. If this was water, this would happen at 100 degrees. Again, during that actual evaporation, the temperature doesn't change very much. You probably saw this the other day when we did the lab. We had the metal and we were boiling the water, and you notice the temperature didn't really change, even though it was boiling off. And that's because that's the evaporation point. At that point, it will stay the same during the evaporation of that liquid. Once it's done, though, if you trap the gas, you can superheat a gas, continue to heat it, and again, the temperature will change. This is if I'm heating the whole thing. But what happens if I cool it down? Remember, if I'm cooling it down, instead of adding heat, I'm removing it. And all we're going to do is build intermolecular bonds instead of breaking them. So it just looks like this. It's the reverse. I have a gas, the molecules are cooled down, they get colder and colder and colder, they slow down because of this, they hit the condensation point, the point at which it will go from a gas to a liquid. At that point, it will stay the same temperature for a little while, and that's because I'm removing that energy. As I remove that energy, those bonds will reform. No temperature change because that's what the removal is doing, is allowing those intermolecular bonds to start to form. They're not changing the speed of the molecules. But as soon as it all becomes a liquid, again, the removal of energy is going to go back into changing the temperature. The temperature will decrease and decrease and decrease until it hits the freezing point. If this was water, this would be at 0 degrees. As soon as it hits that temperature, then freezing starts. Freezing will not take long. All those molecules will hit that 0 and start to reform their intermolecular bonds. At that point, the temperature doesn't change for a little bit. It's not a long period of time, it's short. But during that actual freezing, the intermolecular bonds reform instead of the molecules slowing down, because that's what the energy is doing. The removal of the energy is causing the molecules to reform their intermolecular bonds and not changing the actual speed. But once freezing ends and it's all a solid, it will start changing a temperature again. It will slowly decrease in temperature because you're slowing the molecules down again. That's basically all this is that as the object cools, energy is removed, it condenses, then it freezes, it changes the temperature. But during those times of condensation and freezing, intermolecular bonds, they're going to reform. So